Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this particular video, I will talk about certain terms related to a chapter in S2, that is sampling. So we'll talk about what is meant by sampling, what is meant by the sample mean, and how do we judge the distribution of the sample mean. So first of all, as far as the term sampling is concerned, it's like a very common thing that we are doing in everyday life. Like for example, if I have to taste the flavor of any food, I'm not going to eat the entire food to know how it tastes like. So I'm just going to take a small sample of it and I'll see how the flavor is. So obviously that is something that is very much required in a lot of situations of mathematics as well. So sampling actually means that we take a small proportion, a small size of the entire population to draw a conclusion about the entire population. So like for example, if we say that we are doing sampling, so an example of sample could be that we read few paragraphs of a book to check if there are grammar mistakes in that particular book, or to find out the favorite food in a particular area or in a particular city. It might be very difficult to go and ask every single individual that lives in that city. So instead of going to every individual citizen, what we actually do is that we go to random people. Obviously we will try our best that when we take a sample, that sample should not be a biased sample. So that means that a certain proportion of a population has a greater probability of being selected. So we have to make sure that every member of the population has equal probability of getting selected, and then it will be a fair sample. So an unbiased sample should have an equal probability of selecting, and we can do that by drawing lots. That is, we write down names of the entire population or the group of population onto small pieces of paper, and then we draw lots to select certain members of that particular population. Or we assign numbers to every member of the population, and then we pick some random numbers and call out those numbers. So as far as the sample mean is concerned, that's basically a certain variable in which what we do is that we decide upon a certain size of a sample, and what we do is that we repeatedly take samples of that size and find out their average. Like for example, if I decide that I'm going to take a sample mean of size 5, so that means I take 5 values from the population and find their average, and then take another 5 values from the same population and find their average, and then another 5 values from the population and take their average. So I repeatedly keep on taking samples of a size n and then keep on finding out their averages, which itself actually becomes a variable, and we represent that variable as x bar. We must know that the expectation or the mean of sample mean is actually equal to the original population mean, and variance of the sample mean is equal to the variance of the population divided by n. We have this mathematical evidence for that, and that is if you are finding out expectation of x bar, and x bar itself is x1 plus x2 plus x3 till xn divided by n. And 1 over n can come out of this because we know that expectation of ax is equal to a times expectation of x. So I can move this n outside, and then I will have expectation of x1 plus x2 plus x3 plus xn, and I also know that expectation of x1 plus x2 is equal to expectation of x1 plus expectation of x2. I can write these down as expectation of x1 plus expectation of x2 plus expectation of x3, and so on and so forth. Now x1, x2, x3 are the members of the population, and the population has a mean of mu. So that means all of these variables will have mean mu, which will add up to n mu, and n and 1 over n would cancel out to give you an overall mu, which means that the sample means expected value is equal to the population's expected value. And similarly, we can find out the variance of the sample mean as well. So variance of x bar would be x1 plus x2 plus x3 till xn upon n. Now for variance, we know that variance of ax is equal to a square variance of x. So that is why when I move this n outside, this is going to become 1 over n square. And I also know that variance of x1 plus x2 is equal to variance of x1 plus variance of x2. So that means this is going to become variance of x1 plus variance of x2 till variance of xn. So this x1, x2 and xn are the members of the population itself. So their variance is sigma square. So sigma square plus sigma square, and we are adding sigma square n times. So that adds up to n sigma square, and this n and n cancels out, and I get the variance as sigma square divided by n. So what we are trying to say is that if I have a particular population whose expectation is known to be 25 and variance of that particular population is known to be 3, and I decide to consider a variable that is a sample mean of size 10, then the sample mean represented by x bar would have mean still 25, but the variance will become now 3 upon 10. And I mean, just to give you a bit of an idea of what's actually going on here, let's say you have a data being represented on a number line. And what you're doing is that you're finding out the sample means. So that means that you take a certain set of data and find out its average, and then you take out a certain set of data and you find out its average. So you keep on doing that, and that is what sample mean is. And you will see that the mean of the entire set of data must match with the mean of these average sample means. But if you look at the scatter, you would realize that after finding out the sample means, the scatter or the variance of the data has been reduced, and that's why we also saw that mathematically that the variance gets divided by n. Now, how do you determine the distribution of the sample mean? So you must know that if x, that is the population variable, is known to be following a normal distribution, then x bar will always follow a normal distribution. There is an exception, but that is not part of the S2 syllabus. But the exception is that if you don't know the actual population variance, then you can't apply this. But like every question you'd get, you would be knowing the population variance. So if you know the population mean and population variance, and you know that x, the original population, originally follows normal distribution, then x bar must also follow normal distribution. If you've just figured out that the mean remains the same and variance gets divided by n. But if n is bigger than 30, then the population needs not to be normal. So for all conditions, be it normal, be it some other distribution, be it a population of binomial distribution or geometric distribution or Poisson distribution, it does not matter. If sample size is bigger than 30, then sample mean is always going to be following a normal distribution. So if x follows binomial, and you know that in binomial you find expectation as the product of np and variance as npq. So if you found out the mean and variance of the original population, then you can write down the sample means distribution as mu and sigma square over n. The same thing could be done with Poisson. Let's say, for example, there's a Poisson with mean lambda. So in Poisson distribution, mean and variances are equal. So mean would be lambda and variance would also be lambda. But for x bar, you would know that it should follow a normal distribution. So what you have to identify that if you see that you're taking bigger sample sizes bigger than 30, then irrespective of the distribution of the population, be it any distribution of the population, the sample mean is always going to be following a normal distribution. So in this video, we're going to discuss till this point, and then we'll see how we will apply that onto different situations. Thank you so much, guys. If you found video useful, please do give a thumbs up and do subscribe to my channel.